Hello, Math Studies students. Welcome to our 8.8, 8.9 notes. In this lesson, we are going to learn some ways to help you organize and count outcomes. If you're going to compute probabilities, you have to be able to organize and count your outcomes. So we're going to learn a couple ways to help us do that. So the first one is called a sample space diagram. It's a graphical way of showing the possible equally likely outcomes. Outcomes of an experiment rather than listing them. Okay, of course, listing all the possible outcomes is one possibility, but there are other ways to do that. So let's take a look at an example. Let's say that we have a red dice and a blue dice, and we're going to roll them together. So let's first of all talk about how many elements are in the universal set. What's the total of all possible outcomes? Well, the red dice has 6 faces and the blue dice has 6 faces, and 6 times 6 is 36. So there are 36 possible outcomes, okay? So what we're going to do is use these sample space diagrams to help us find some probabilities. Like, for example, let's find the probability that the total score is 7. So we have the possible outcomes for the red dice, 1 through 6 here. We have the possible outcomes for the blue dice, 1 through 6 here. So all of these dots represent an individual equally likely outcome. So what we're going to do is we're going to just circle all the ones where the total score is 7. So for example, this dot would be what the outcome of rolling a 2. You've rolled a 1 on the red dice and a 1 on the blue dice, so this one is 2. Or for example, this dot, let's take this dot. This dot would be the outcome of rolling a 7 because you've rolled a 3 on the red dice and you've rolled a 4 on the blue dice. So let's find all of those where the total score is 7. So I'm going to find dots where the red plus the blue would equal 7. So this is 2, this is 3, 4, 5, 6. Here, this dot, the red dice was a 1, the blue dice was a 6. So that's a 7. We're going to circle that one, okay? So how else can I get a 7? Well, I could also roll a 2 on the red and a 5 on the blue. So I'm going to circle this one. And then this one would be a red 3 and a blue 4. Here's a red 4 and a blue 3. A red 5 and a blue 2, and then a red 6 and a blue 1. So those are all the possible ways that we could roll a 7. So if we count what we've circled, you get a total of 6. And so the probability of rolling 2 dice, a red and a blue, and getting a total of 7 would be 6 out of a possible 36 outcomes. Okay, how about this next one? The probability that the total score is even. So I think you can probably already tell me that this would be 50%, but let's see how that works out visually. So I'm going to circle this outcome because 1 plus 1 is 2. I won't circle this one because that's an odd outcome. A red 1 and a blue 2 would be 3, but this would be 1 plus 3 is 4. Okay, and then an outcome of 1 and 5 is 6. Then when I roll a red 2, I'll get evens if I roll a blue 2, a blue 4, and a blue 6, so I'll circle those. Okay, when I roll a 3 on red, I'll get an even outcome when I roll a 1 on the blue, a 3 on a blue, a 5 on the blue. And then when I roll a 4 on the red, I'd get an even outcome when I roll even blues. Okay, when I roll a 5 for the red, I'm going to get an even outcome when I roll odd blues. So 5 plus 1, 5 plus 3, and 5 plus 5 would all be even. And then when I roll a red 6, I'd get an even outcome when I roll an even blue. So that would be when I roll a 2, a 4, or a 6 on the blue. So as we suspected, look at this visually, you can see it looks like we've circled half of the dots, and if you counted, you would get a total of 18 out of 36. So our suspicions were correct. Okay, how about letter C? The same number is rolled on each dice. Okay, so that would be a 1 when we get a 1 on the red, a 1 on the blue, a 2, and a 2. So those outcomes would look like this: a 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So we count those. We can see that there are 6 ways that can happen. So our probability is 6 out of 36. All right. Letter D says the difference is 1. Okay, so I have to think a little bit more here. Okay, so the difference is 1. When I have a red 1 and a blue 1, that difference is 0. Here we have a difference of 1 because blue 2 minus red 1 is 1. So I'm going to circle that one. I'm also going to, I think that's all the only way I can, when I roll a red 1, that's the only way I can get a difference of 1. When I roll a red 2, I can get a difference of 1 if the blue is 1 or the blue is 3, because 3 minus 2 is 1 and 2 minus 1 is 1. When I roll a red 3, I can get a difference of 1 when I roll either 2 or 4 on the blue. When I roll a red 4, I can get a difference of 1 when I roll either 3 or 5 on the blue. And then when I roll a red 5, I can get a difference of 1 when I roll either a 4 or 6 on the blue. And then when I roll a red 6, the only way I can get a difference of 1 is if I roll a 5 on the blue. Okay, so we count that. So when we count up the possible outcomes, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So first of all, we need to change, there's a typo here. This should say difference of 1. So if you can change that, we can see that there are 10 out of 36 ways of rolling the two dice and getting a difference of 1. Okay, how about this one? The score on the red is less than the score on the blue. So that's going to happen, let's see, it's not going to happen here, but it would happen here where our red was 1 and our blue was 2. Okay, so when red is 1, then as long as blue is bigger than 1, we're good. Okay, when we roll a 2, as long as blue is bigger than 2, so that would be here, 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 and here. And then when we roll a 3, blue would have to be 4, 5, or 6 in order for us to have the blue outcome bigger than the blue outcome. When we roll 4 on the red, then that means blue would have to be 5 or 6. And we roll a 5 on the the red, then blue would have to be 6. And then, of course, if I roll a 6 on the red, there's no way I can roll a blue one that's bigger. So if we count these up, that would be a total of 15. So there are 15 out of 36 ways of that happening. And then this last one, the total is prime. Okay, so let's see. We're just going to have to go through them one by one. Let's see. 1 and 1 is 2. That's a prime number. This would be the outcome of 3. That's prime. This is an even. Let's see. This one's prime because 1 plus 4 is 5. And I think that. Oh, and then if I roll a red 1 and a blue 6, that would be prime. If I roll a red 2 and a blue 1, that would be prime. A red 2 and a blue 3 is prime. A red 2 and a blue 5 is prime. And then when I roll a 3 and a 2, that's 5, so that's prime. And then 3 and 4 would be prime. 3 and 6 is not prime because that's 9, and that's not prime. Okay, when I roll a red 4, then when I roll a blue 1, that's prime because 4 plus 1 is 5. And when I roll a 3, that's prime. Let's see, 8, 9, 10. That's it for 4. When I roll a red 5, then a blue 2, that would be 7, which is prime. 8, 9, 10, 11. When I roll a red 5 and a blue 6, we have a prime. And then when I roll a red 6, I could get 7 or 8, 9, 10, 11. Looks like that's it. Okay, so count up all those outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's 15 out of 36 ways that we can roll a prime number. Okay, so now what we're going to do is take a look at a different type of visual representation of showing probabilities. So this next one's called a tree diagram. You've probably done tree diagrams before. It's another graphical representation to represent and calculate probabilities. So let's take a look at this example. 2 fair dice are rolled, one's red and one is blue. Using the tree diagram, find the probability that these things happen. Now, if you look at our probabilities, getting a double 6 or no 6s, so this all have to do with 6s. Okay, so let's look at all the possibilities. So if I roll the 2 dice, what could come out on the red? Well, we're only interested in 6s now, so I would either roll a 6 or I would not roll a 6, okay? So on the branches of our tree, let's write the probability for both of those outcomes. On the red dice, rolling a 6, there's one way out of 6 that can happen. So let's put 1/6 right here. And there's 5 ways out of 6 that you would not roll a 6, okay? So those are the 2 possible outcomes for the red, okay? Now, for each of those outcomes, there are 2 outcomes for the blue. So if I get a red 6, then I could either get on the blue, a 6 or not a 6. Okay, so that probability of the blue dice, there's 1 out of 6 ways I would get a 6, and there's 5 out of 6 ways of not getting a 6. Okay, and then to finish off our tree, if we roll something that's not a 6 on the red dice, then the blue dice could either be 6 or not a 6. Okay. Now, again, that probability of getting the 6 on the blue dice is 1/6, and the probability of not getting a 6 on the blue dice is 5 out of 6. Okay, so now, let's go ahead and list all of our possible outcomes. So I could either get, you know what, I'm going to do this in color to help us out. We can get a red 6 and a blue 6, okay? If I follow this branch, I've got a 6 and a 6, or I could get a red 6 and a blue not 6. So red 6, it's supposed to be 6, and then blue not 6, okay? Let's follow this path. We can either get a not 6 on the red and a 6 on the blue. So this would be not 6 for red and 6 for blue. And then the last possible outcome is getting not 6 on the red and not 6 on the blue. So not 6 and not 6. Okay, so now to calculate those probabilities, we'll just multiply. So the probability of getting a 6 and then another 6 is just 1/6 times 1/6. So that's 1/6 times 1/6, which is 1 out of 36, okay? The probability of getting a red 6 and a blue not 6 would be 1/6 plus 5/6. So 1/6 times, I said plus, I meant times, 5/6, which is 5 out of 36. The probability of getting a red not 6 and a blue 6, that would be 5/6 times 1/6. So 5/6 times 1/6 is 5 out of 36. And then last but not least, the probability of getting both of them not 6 would be 5/6 times 5/6. And 5/6 times 5/6 is 25 out of 36. Okay, so now we can answer these questions. So what is the probability that a double 6 is rolled? Well, that's right here. That probability is 1 out of 36. We've already calculated it. Okay? And then the probability that no 6s are rolled, okay, that would be here. That would be, we've already calculated that. That's 25 out of 36. So 25 out of 36. Okay. The probability that exactly one dice is rolled. Well, that can happen two different ways. It can happen here or it can happen here. So we have to add those two probabilities together. So that's going to be 5 out of 36 plus 5 out of 36, which would be 10 out of 36. Okay. And then letter D says find the probability that at least one 6 is rolled. Well, at least one 6 was rolled here, at least one 6 was rolled here, and at least one 6 was rolled here. So we have to add all three of these probabilities. So that's going to be 1 out of 36 plus 5 out of 36 plus 5 out of 36 for a total of 11 out of 36, okay? And then for this next one, it's a conditional probability question. It says, given that at least one 6 is rolled, find the probability that the red dice shows a 6, okay? So the red dice shows a 6 given that at least one 6 is rolled. So I just want to, I know you don't have room on your paper, but I just want to remind you of the rule for conditional probability. The probability of A given B is equal to the probability of the intersection of A and B over the probability of B. If you'll remember when we did these in Venn diagrams, we looked at the intersection of two sets over just one of the sets. And so let's apply that here. So what we're being asked to find, and I know you're not going to have quite enough room, so prepare to write small. We're going to find the probability of getting a red 6, so a red 6, given that we have at least one 6, okay? So to find that out, well, we're just going to apply this property here. The probability the probability of both things happening, of being a red 6 and at least one 6. So, and let me write out what we're going to do. We're going to take the probability of a red 6, the intersection of that with at least one 6, all right? And then we're going to put that over the probability of getting at least one 6. And I apologize, you're running out of room on your paper, I know. Okay, so let's find this top probability. So the probability of getting the intersection of a red 6 and at least one 6. Now remember, an element is in an intersection if it's in both sets at the same time. So if we look at this outcome, this is we have a red 6 and at least one 6. We also have a red 6 and at least one 6 here. So we're going to have to add those two probabilities together. So we're going to have 1 out of 36 plus 5 out of 36 in the numerator of this fraction, and in the denominator we need to put the probability of at least one 6. Well, how can that happen? We have at least one 6 here, we have at least one 6 here, we have at least one 6 here, so we have to add all those together. So that would be 1 out of 36 plus 5 out of 36 plus 5 out of 36. Now again, I apologize, I know you've run out of room on your paper, but I'm going to go ahead and keep writing. So we have the numerator would simplify to 6 out of 36. The denominator would be 11 out of 36. Now if you remember your grade school arithmetic, this is called a complex fraction. And dividing by a fraction is the same as multiplying by the reciprocal. So this is the same thing as 6 out of 36 times 36 over 11. So those 36's will cancel, and our final answer is 6 out of 11. Okay, and again, I apologize. I know you don't have room for all that on your paper. Okay, so now we're going to take a look at a new type of probability problem, and we're going to use a tree diagram to help us solve it. So this is what we call a without replacement problem. So here's a classic type of example. There are 6 peppermints, we're going to call those P, and 2 licorice, we're going to call those L, candies in a bag. A candy is picked out and not replaced in the bag. We haven't done a problem like this yet. Then a second candy is picked, and then we're going to find some probabilities. So we're going to first of all make a tree diagram to represent all the possible outcomes of pulling one candy out, not putting it back, and then pulling a second candy. Okay, so let's talk about that first pick. So when we first pick something, okay, kind of go down a little ways on your paper and draw the 2 possible outcomes for your first pick. Your first pick can either be peppermint or licorice. So I'm going to label this first pick. Okay, now there are 6 peppermints and 2 licorice, so there's a total of 8 pieces of candy in the bag. So the probability of picking that peppermint the first time would be 6 out of 8, and the probability of picking the licorice would be 2 out of 8. Now, once you've picked that first piece of candy, then you're going to have a second pick. So the second pick can either be, when I get a peppermint the first time, I can either get a peppermint or a licorice. And then if I pick a licorice the first time, the second one, again, could either be peppermint or licorice. So now let's talk about those probabilities. But you have to remember, this is without replacement. So we picked out a piece of candy. We did not put it back. So now, after that first pick, when we talk about the second pick, okay, then we're talking about now only a total of 7 pieces of candy in the bag. So if I have picked a peppermint, the probability of picking a second peppermint, well, there were 6 peppermints, but I've already picked one, so there's 5 peppermints left out of 7 pieces of candy. So that probability is 5 out of 7. Now, the probability that I pick a peppermint and then a licorice, okay, now this probability again, this licorice, there's still both licorice pieces in the bag, but there's only 7 total, so that probability is 2 out of 7, okay? The probability of picking a licorice and then a peppermint, well, there's still, if I've picked the licorice the first time, all 6 peppermints are still in there, but there's only a total of 7 pieces of candy left. And then the probability of getting a licorice that second time if you've already picked a licorice. There's only one piece of licorice left. There's only 7 pieces of candy left, so that would be 1 out of 7. Okay, so let's list those possible outcomes. Okay, so the possible outcomes are, I can just follow the branches of the tree. I can get a peppermint and a peppermint and a licorice, a licorice and a peppermint, or a licorice and a licorice. So our possible outcomes are PP, PL, LP, or LL. Okay, so now let's see what we're going to find. We're going to find these probabilities. Let's find the probability that A, one of each type is chosen. Okay, so for letter A, we're going to find the probability that one of each, oops, oh, you know what, before we do that, let me erase that, I'm so sorry, I forgot. Let's go ahead and calculate all the possible probabilities. Okay, probability. Okay, so the probability of getting a peppermint and then a peppermint, just follow the branches of the tree. That would be 6/8 times 5/7. So 6 over 8 times 5 over 7 would be 30 over 56. We're not going to take the time to simplify these, but of course you could. The probability of getting a peppermint and then a licorice would be 6/8 times 2/7. So 6/8 times 2/7 would be 12 out of 56. Okay. The probability of getting a licorice and then a peppermint would be 2/8 times 6/7. So that would be 2/8 times 6/7, which is 12 out of 56. And then the probability of getting a licorice and then another licorice would be 2/8 times 1/7. Okay, 2/8 times 1 out of 7, which is 2 out of 56. Okay, so now let's answer the questions. Okay, the first one was find the probability that one of each type is chosen. Okay, so I'm going to have to scroll up a little bit. Okay, so letter A was find the probability that one of each is chosen. Okay, well, there's 2 ways that can happen. We can get a peppermint and a licorice, or a licorice and a peppermint. So we'll add these 2 probabilities together. So that would be 12 out of 56 plus 12 out of 56, which is 24 out of 56. And again, we're not going to worry about reducing to save us a little bit of time. Okay, letter B then is a conditional probability. So let's take a look at it. It says, let's see, given that one type was chosen, find the probability that the first one was a peppermint. So given that one type was chosen, find the probability that the first one is a peppermint. So let's use the definition of conditional probability to help us. So what we're being asked to find is the probability of the first candy being peppermint, given that we have one of each. Okay, oops, that should be a parenthesis, sorry about that. Okay, so that means we're going to find the probability of the intersection of the first one being a peppermint, and we have one of each, okay, over the probability of getting one of each. Okay, so the probability of the intersection of the first one being a peppermint and having one of each. Well, we can see that there's only one way, there's only one way that could happen, and it's right here. The first one being a peppermint and getting one of each. So that probability was 12 out of 56. Okay, so we will put 12 out of 56 in the numerator of that fraction, and then put that over the probability of getting one of each. Well, remember, that was 12 out of 56 and 12 out of 56, because there were 2 ways that could happen. So we have 12 over 56 over 24 over 56. So what I'm going to do is rewrite that as a multiplication problem. That would be the same thing as 12 over 56, the numerator, times the reciprocal of the denominator, 56 over 24. Those 56s will cancel, and we get 12 over 24, which of course reduces to 1/2. All right, if you have any questions, be sure and ask me in class, and we'll be doing some practice problems over this in class.